I want to go over the distance, total line travel, displacement, distance in a straight line, right? So straight line distance from start to finish. So just remember this. If you start here and you travel all this distance here and you finish here, right? You start at here and you finish at P. That total length, right, that you travel, that is called your distance. The scalar quantity as well. But a straight line distance from here to here, where you start to where you finish, that is called your displacement, right? No. Right? That is called your displacement, right? Speed is a ratio of distance on time, scalar quantity, velocity, right? As displacement divided by time, SI unit, same SI unit, but velocity is a what? Is a vector quantity, right? So please remember this, right? If I have an object, if I have a right, if I have an object going this way, right, and the speed positive, then if the object going in the opposite direction, the speed is negative, right? So remember that velocity is displacement per unit time, and it's also a vector quantity. All right. The velocity is constant if it moves at a steady speed in a straight line or changes direction, or the velocity will change, right? So remember this. If I give you a circle, and an object moving in a circle, at every single point, the direction changes. And we just learned that once direction changes, the object velocity is also changing, right? So remember that, right? Once the direction changes, then the object has a velocity, right? Velocity changes. Okay, that's some small things to remember. How do we convert kilometers per hour to meters per second? Right? All we have to do, multiply by 1,000, divide by 3,600. Or you can multiply by 0.27. Okay, so to go from kilometers per hour to meters per second, right? You multiply by 0.27 or multiply by 1,000 divided by 3,600. Okay. Meters per second, kilometers per hour to the reverse. Divide by 1,000, multiply by 3,600, or you can multiply by 3.6. Okay. This is a quick trial. Let's do me a favor. Take 100 kilometers per hour and convert it to meters per second. Come away again. Convert to meters per second, thermometry. Any method you want, right? Take kilometers per hour and convert it to meters per second. What you got? 27, right? You multiply by 0.267. And the reverse is multiplied by 3.6. Check it and make sure. Take 27 and multiply by 3.6 and see what you get. It should get close to 100, right? Yeah, you kind of wrong though. All right, nice. That's something great to remember, right? Nice. So now that we can convert one to the next, we need to remember about acceleration, right? Acceleration, right, is the rate of change of velocity. So for example, if I have an object, right, let's say a car, and the car is traveling in this direction. The only way that car will have an acceleration is if its velocity change. So if the velocity here was u and the velocity here is v, then the change in velocity, v minus u, divided by t, that is the acceleration, right? What would have happened if the velocity stayed u? Same thing. Well, what will be the acceleration? 0, right? The acceleration is 0. Okay? So the only way an object can have an acceleration is if it changes, right? If the acceleration is negative, we call it deceleration. Okay? So those small things, make sure you remember them, right? If the object has no velocity changing, or velocity staying the same, has no acceleration. If the velocity negative, if the acceleration negative, it's deceleration, right? All right. There's some small things to remember. Right, graphs. Remember, you have two types of graphs. You have a displacement time graph, like we have here, and we have a velocity time graph. In a displacement time graph, anybody remember what the gradient represents? What's the gradient for a displacement time graph? The gradient for either of these graphs is velocity. Right? Any graph, any displacement time graph, the gradient is velocity. Okay? Here the velocity positive, here the velocity negative. So what does that mean here, Olivia? What does that mean? The velocity here positive and the velocity here negative. Huh? Could be, but not. You can't really tell that from the type of graph. What does that change in sign and velocity give you? I told you a little while ago, well, a few minutes ago. Anybody? Yes, somebody say that. Change direction, right? So it means in the first 2 seconds, right? It changes direction in the last second compared to the first 2, right? What does this horizontal lines here say? Gradient is 0. Horizontal line, remember in the amplitude, horizontal line means the gradient is 0. What does that mean? Object moving? No. Right? If the gradient is 0, it means that your velocity is also 0. All right? And then in the last graph, the velocity time graph, right? In your velocity time graph, the gradient of the graph is the acceleration. Right? So the gradient of a graph like this is the acceleration, here positive, here negative. Right? We know positive means accelerating, negative means decelerating. And if your gradient is 0, it means that your object has no acceleration. That's okay? It's moving, but no acceleration. All right? So those are the things that we needed to remember from time graphs. Okay? And one last thing. Anybody remember the last thing from time graphs? If I give you a velocity time graph, this area here represents something. What is this? Distance covered. Right? So distance covered. All right? Okay, nice. So those are the things that we looked at, right? We're gonna spend some time on Newton's laws now, right? But I want to get that simulation clear to see a few things. If we can use these previous ones, yes. But give a speech entirely by subscribe this now. I don't know. Take it that way. I'm free. Yeah, password. All right. So let's see if we can. Yes. Right. If you look at this simulation here, right? This I'm not trying to use Newton's first law here as well, right? So Newton has three main laws, right? We'll take a look at what the guys before Newton said, Aristotle and Galileo as well, right? We'll look at what those guys said as well. But let's see what happened here. Look at the subject, right? Is the subject moving? No. So our object at rest will stay at rest, right? What will make this object move today? A force, right? So if I were to push it, right, with a net force of 10 Newton, is see what will happen. It will move. Okay? So an object at rest will stay at rest unless a force makes it move, right? That's technically Newton's first law. Watch this here. What was the force just now to move it? 10 Newtons, right? Let's go up a little bit. Let's go to about 5. Okay? Push it in. Take it a little slower, right? But the force will move it, right? I want to show you something. So in order, right? In order for us to move it that same speed, right? Watch right here. Give it a little smoother. I might be able to see the pull on that. Right. Watch your speed it covering with 10 Newton, right? Watch your speed. Right? And then let's up it a little bit, right? To 50. Speed increase. Speed increase it. So the larger the mass, the larger the force needed to maintain particular speed. That's okay? So what you can say about the larger the object, the larger the object, the bigger the force needed to make it move, right? That makes sense? Yeah. So that's the basis behind Newton's first law, right? Newton's first law says that an object will stay at rest or keep moving unless an external force makes it behave different. Okay? That's the principle behind Newton's first law. Let's take a look at Newton's second law. Okay, Newton's first law, right? And next word for what we're trying to explain here is called inertia. The bigger the mass, so the larger the mass, right? If I put the largest, right? The bigger the mass, the bigger something called inertia. Because a bigger force is needed to move it, right? Let's check out Newton's second law now. If I were to push it, force, velocity. Just see that? If I were to change the mass, same force, and then I'm changing mass a little bit. What's your velocity? A little bit smaller. Let me calculate that thing quick. Now, let's calculate now. But there's a force. Can anybody remember what the gradient of a velocity time graph gives you? Acceleration. Right here? So here's what you're observing. You're observing that, is that right? You're observing that if I apply a force, I am also getting an acceleration. That's okay. So what Newton's second law says is that whenever there's a net force, right? Once you have a net force, there will always be an acceleration. And they are both. I want you to tell me if it directly either proportional or inversely, right? So what you say here? Right? I am going to decrease the force and tell me what you recognize about the slope, if the acceleration is more or less, right? Same mass. Let's make the force smaller. Let's make this like that. Same. Tell me what you recognize about the velocity. What you recognize? Smaller force means what? Smaller acceleration or not? Yeah. If I were to find the gradient of this, and it'll be smaller. So therefore, when I drop the force, I am also dropping the acceleration. Sorry, come on, I'm bad. What kind of relationship is that, Hishish? That's good. Now, if I drop the force and the acceleration drop, what type of relationship is that? Direct proportional or inverse? Directly. Inverse is the other way around. Okay? So what Newton's second law says is this. Newton's second law says that the net force is proportional to the acceleration. That's okay? And then it's summarized by a nice formula that you will use. You've been use it already. But a nice formula, F is equal to ME. You recognize that? You all use this already to find weight. Weight is equal to mass by gravity. Okay? Mass by acceleration gravity. Are you okay with that? That's been done second. Okay? I don't think I can show you third law again. I don't know, that's what come out of this. Yeah, you can create on both sides. I want to get it into, yeah, I'm showing that out. Or just let's check out it done third law again. Video. But I'll explain what we're doing on there, right? For us, I want to show you the simulation. Then one with something called a Newton cradle. You ever saw a Newton cradle before? Alright, and then jump straight into cradle. Right. Can I reduce the number of balls? Alright, this one I'll let me change. But what's your thing? So here's the principle behind Newton's third law. If I were to displace this ball like this, what you think will happen? It will. Next side. So the purple will move. Yeah. Yeah. So if I were to displace it here, yes, only one will move. Right? If I were to displace two instead, how much will move? I have to coordinate this. I'll pause it. To reset this thing. Huh? Let's see. Oh. Right there. Alright. Okay, so if I were to displace two, alright, now it's okay. What is happening there now? Oh, right? If I were to displace two, what will happen there? Right? Anybody can make a follow? What happened there? Okay, well, you know the law. So every action has an equal but opposite reaction. Okay, so what happening here is that these two masses applying a force here, and there's an equal and opposite force here. Right? When the force applied here, you will see this will move away, come back here and apply the same force. All right. So basically, here's what happened. Let's call those two balls E and let's call these two B. There's a force applied by A and there's a force applied by B and they are equal, but in opposite direction. Okay. If you were to touch the wall, you are applying a force to the wall and the wall applying a force back to you. Right? That's Newton's third law. Okay with that? If we go back to the thrusters example, anybody can explain how Newton's third law applied there? Why is that guy able to basically levitate in the air using the water? Take a Newton's third law. So think of who applying the force, what applying the force, and what receiving the force. So something has to be applying a force, something applied back in the opposite direction. Right. Okay. So basically, the water that coming out from clusters applying a downward force onto the ocean bed, and the ocean bed applying a equal and opposite force onto the jetpack which attached to the guy. That's okay. So that's the principle of how it works. Anybody think of our next example that's similar to that? Something else that behaves just like that. You're probably, I showed them to earlier. Yes. A plane for a rocket is one, but something else. A trampoline, okay, yeah. You apply a force on the trampoline, but trampoline is a little bit different because it's elastic. So the force you apply is a larger force being applied. Same principle. But something else I surely would have done it. Oh, let me narrow it down. All right. I'll just play with the decoration. Decoration. And I'll show you blowing it up once and then a balloon. Right? So you're blowing up a balloon and then you release and you didn't tie it up, then you release it. What will happen? The air coming out applies a force and then an equal and opposite force on the balloon. That's okay? All right. Okay, before we move on, just do my one little favor now. Right the three doors. That's some of them might never open their hand out again. Right, just do my favor and write out Newton's three laws put from the handle. Yeah. Right. You have a question that we have to answer. Why did green not move it? Yeah. Right, yeah. Yes, I know I should write down the laws because those definitions you have to learn them, right? You'll also notice that I have a little summary there. Newton's first law is called the law of inertia. Newton's second law is F equals ma. And Newton's third law is a little formula I have here. This whole thing here, that is summary for Newton's third law. Okay? All right. Have at least zoom in, and I don't know why I can't zoom in there so good, right? But here are some examples of Newton's laws. Okay. So for example here, example of Newton's first law, this object will stay at rest, right? Unless acted upon by a net force. What do you think happening here? Who's with the same guy, right? What else think happening here? The object will move? No. What about here? The object will move, right? So the guys will exert a force that will cause the object to move. Watch this here. A ball is stationary. When you hit the ball will go up in the air and then come back down. So this ball moved because a force was applied to it. Why the ball came back down? Because of the effect of gravity, right? So the force called weight pulled the ball downwards. That's okay? Oh, I'll come back to Newton Fatal lesson. Right? Newton's right? Here we have a example of Newton's second law. You're seeing small acceleration, large mass, right? And here you have large acceleration, small mass. What we're trying to show here. Remember, force is equal to what? Force is equal to mass multiplied by acceleration. So what it's saying here is that these two objects have the same net force acting on them, right? A large mass of the elephant with a very small acceleration can give you the same force as a small mass with a large acceleration, right? Let's play around with some numbers and see if this makes sense, right? let's say the elephant has a mass of 1,000 kilograms, right? And the acceleration of the elephant, let's say the acceleration is real small, right? Let's say the acceleration is 1 meter per second squared. What is the net force acting on this elephant? 1,000 newtons, correct? The net force will be 1,000 newtons. Have you okay with that? Yeah. Force by mass, sorry, mass by acceleration, right? Or we put the SI, right? Online, are you okay? Right? Let's look here now. Let's say we have a small mass, let's say about 2 kilograms. Right? But we hit this ball real hard, right? So the acceleration has a large acceleration. Let's say the acceleration is 500. Right? 500 meters per second squared. Then what will be the net force of the ball? 2 multiplied by 500, which is 1,000. Right? So what this example is trying to show is that they both have the same net force, although they are two different masses. Okay? Two different masses giving you the same net force. Are you okay with that? Yeah. And of course, you see the main reason why is that this large force can only obtain a small acceleration with this force, while this small mass can obtain a large acceleration with the same force. Okay, so that's Newton's first and second law. And last thing, Newton's third law. These laws, almost everything you do in everyday life, you can see these laws, right? And Newton's third law, right? See that here? Downward force applied by the air coming out equal upward force applied onto the balloon and the balloon will go. Right? But of course, if the air coming out in all different directions, the balloon will move in all different directions. Right? And here you have a hammer applying a force on the nail. Right? If the force of the hammer larger than the force needed to penetrate the brick, the nail will go to the brick. Okay. All right. So all those are examples of Newton's laws. Okay with that? Right? So you have to be able to see how Newton's laws apply, right? Anybody remember the example that we did? What would you play? Up back here. Right. Do I have to share? Theory. Hold on. Yeah. Back. Right, online holiday still. I only had one response to the whole class from the research. Holiday still, right? Ali, Aliyah, holiday. All right, so as I said, first law, the summary for the first law is what we call the law of inertia. Second law, summary, in net force is equal to mass by acceleration. Third law, two bodies will exert a force, right? And the forces are equal, but in opposite direction. All right. So we're gonna use these laws here, and we're gonna look at a new quantity. A new quantity is called momentum, right? It's a word that we use all the time, right? And we want to investigate what is momentum. right, Caleb? So if I give you a mass, does that have momentum? When I think about momentum, what do you think about? Something like what? Something that moving, right? So if I give you a mass and that mass moving with a velocity v, it has something that we call linear momentum. Right? The linear momentum of this object is the product of its mass and its velocity. You gotta remember Newton's cradle, right? The little ball, right? As the little ball moved, it had a momentum, right? It had a momentum that was equal to its mass and velocity. What would the SI unit be? What's the SI unit here? Children? What's the SI unit? Look at it here. Mass is in what? Kilograms, and velocity is in what? Velocity is in meters per second, right? So linear momentum is kilograms per meter per second, right? That's the SI unit. So this new quantity, linear momentum, we observed it here and here. And we want to see how come, right? In a little while, I'll show you. Okay? Right. One thing that we need to note is that momentum, the symbol for momentum is a lowercase p, right? Right? Momentum is a vector quantity. Right? So what it implies is this. If I gave you a momentum with an object, mass by m by v, the momentum of this object is mv. But if I gave you a mass going in the opposite direction, same v, it has the same momentum, magnitude, m by v, but its direction is opposite. That's okay? Are you okay with that? So momentum changes. Momentum changes here because the direction changes. Okay? Same mass, same velocity. Same mass, same velocity. Right? But the direction change. Right? While you're writing, right? If these two masses were to collide, what do you think will happen? Same mass, same velocity. What do you think will happen? When they collide, they will stop. All right. So we will see why. That's correct, right? So when these two collide head on, something will happen, right? And we're going to take a look at that, right? Copy this down. Oh, I was asking about the plane example that we did. Anyway, most likely we will do it again. That's Did you have that? Right. So basically, this new quantity that we call momentum is mass by velocity. That's all, right? Momentum is mass by velocity, right? So we're gonna take a look now at something called conservation of time, right? Let's wait, now see different is sending message. Yeah. All right, so good. So we want to take a look at what is this conservation of momentum, right? Online, are you okay there? Ethan, pay attention. Ethan. Okay, good. All right, Ethan. Someone else say you are important message. Alright, so what's the thing? So we're going to take a look at something called conservation of momentum, right? So it's a law that applies whenever objects collide. Okay, so let's change it up. Let's make sure they have the same mass here. That's good. Same mass. What a line mean? Right, it gave us how we can control the velocity. So what? Alright, now get the control the velocity. Hold on there, William. I want them to have the same velocity. Wait, so move it. I was saying, everything control this velocity. More data, need more data. More data. We control this here. Right. So here's what we have here. This is the scenario that we were talking about, right? We have a mass. We have same mass here. They both have 0.5 kilograms, and they both have the same velocity in opposite directions, right? So just do a quick favor mentally, do it mentally. What is the momentum of the collider? Like look. Steel. Right. Work out the momentum here of the teal and work out the momentum here. Think it will confusion. Right? Work out the momentum of the teal and work out the momentum of the teal. Tell me what you get. You can do it mentally. Alright. So we must say that the teal is 0.5. I can't fit the SI unit, right? And the momentum of the pink is minus 0.5. Why do we have to leave the minus sign? Going opposite directions, right? So Sadiq, when I play here and I allow them to collide, what do you think the momentum? What do you think would happen to the object? They'll move away. Yeah, they'll move away. Anybody have a different answer? Javi, what do you think? As well? Moving up the directions. They will stop. Anybody else? Scenario? No answers? Nothing happened? Right? So let's see, they both have the same momentum in opposite directions, right? So I'm going to play it there. What else see online? Let me just see you waiting online. Online. What will happen? Would they move off in opposite directions or would they stay one place? Let's see what online saying. Online message answer, please. Would they stay one place or would they move in opposite directions?
Everybody on written on all yet? And Nathaniel said opposite directions. Larissa said opposite direction. Annalie, Leah, Ethan. Everybody else? Aliyah said Steve. All right. While you're waiting on the rest of them, let's see what happens. That was supposed to happen. Fully elastic, right? That's supposed to happen, right? Right. So when they collide, it's supposed to stop. And here's why, right? There is a law called the conservation of momentum that says the total momentum before they collide is equal to the total momentum after collision, right? So let's do a little math here. What is the momentum before they collide? Let's add these two, right? 0.5 plus minus 0.5 is equal to how much? So it means that the momentum after should also be. That's okay? That's okay? So the answer is they're supposed to stop. All right? Let's change the scenario slightly and see if we could observe the same thing, right? Hold on. I'm going to up the mass a little bit. Let's put the mass as 1, right? Let's give them the same velocities. Let us reset. There, reset everything. I can't move the balls. If you put the velocity there, then they can move away. All right. So watch this here, right? All right. So watch this here. Let's watch some more, get some more data. So the velocity is 1 and minus. Here is this and this, right? Let's do one quick favor now. We've got the momentum on the tail for now. Momentum on the tail is what? So that's 0.5 by 1, right? So that's 0.5. That's before collision, right? And then work out the momentum of the pink. Momentum of the pink is what? Negative 0.7. Nice. Are they equal? No. Who has the larger momentum? The pink or the teal? Pink. So when they collide, which direction do you expect them to move in? The direction of the pink, right? Do my favor, out of these two, tell me what you get in momentum. Add them up. 0.5 plus minus 0.75 should give you negative 0.25. Let us see now when they collide, if that's the momentum they'll move off with, right? Hold on now. See that? Right? So the momentum, this is the momentum before. Yes, we have some much to do again. This is the momentum before. Now let's see if we can work it out after. Right, cut out here. What's the momentum and T after? Multiply those two. Minus 0.3 by 0.5. Multiply its speed minus 0.3 minus 0.3 by 0.5 is how much? Minus what? How much? Look shop. Oh, I wasn't watching. Minus 0.06. And the momentum of the pink is also minus 0.19. Okay? Add them up, and you will get minus 0.25. What does that say? That says that the momentum before equals the momentum after. You see that? So that's the principle of conservation of momentum. Okay. Also, you might recognize that these two balls stick up together. Right? If a question says that they stick up together, they'll move with the same velocity. Everybody okay with that? All right. Okay, so that is your principle of conservation of momentum. Right, stop share. Back to the board analysis. Yeah. All right. Let's do one question that we might have. Go back to it. Right, let me just go back to the Newton cradle quick. All right. So let's go back before we answer the question, right? We're going to also observe the conservation of momentum here. Okay, watch this here. If I were to move this ball back, momentum there is mass by the velocity of that ball, right? Correct? So if I were to allow the ball to hit the yellow, how much ball should move off? Yes, one. Because the momentum before is momentum equals the momentum after. The momentum here equals momentum there. That's okay? If I move two balls before, momentum before equals momentum after. Okay? If I move the momentum here and momentum here, it should be the same. If I move three balls, what do you think will happen? Three should move off. Momentum before should always be equal to momentum after. But Rima asked a question, right? Why that green ball not moving? Two ways you can answer. The first way is different momentum. If that green ball move, and the momentum will be different. Momentum before would be equal to momentum after. So that's law number one. And number two is when the yellow applies a force to the green, and the green applying that to the blue. So it kind of being transferred, right? The transfer, we have to combine all the loans. We have to combine them. So basically, two things balancing out. Yellow applying to green, green applying to yellow. That balancing out. And then green applying to blue, right? And blue applying back to green and then balancing. But there's two balls in front. There's a larger, so it's larger. right? So, but I showed you to look at it, if the force being applied, just basically keep it in neutral. Are you okay with that? So that's the principle of momentum, right? All right, nice. We're almost done. We're almost done. No major calculation. Next day we will do the past papers on this. All right. But just take a small note for this. Conservation of momentum. When two or more bodies collide, when two or more bodies collide, when two or more bodies collide, or indeed when two or more bodies collide, their total momentum before collision, their total momentum before collisions is equal to the total momentum after their collision. The total momentum before collision is equal to their total momentum after collision, provided that no external forces are. Provided that no external forces are. Right, copy this down there. Alright, sorry there. So let's see if we can apply this calculation, right? So I'm doing a small example. I just put in some numbers to the same thing that we are doing, right? Let's say I gave you a ball of mass 4 kilograms and a next ball of mass 3 kilograms. One going this way with a speed of 3 meters per second, and one going this way with a speed of 5 meters per second. Right? They are along the same path, so they'll collide. This is before. And then after collision, 4 kilograms here, 3 kilograms here. Right? They both move off in this direction. Right? I don't know the velocity this one move off with, but I know this one. This one is above 2, right? Let's pretend it's 2. Let's assume they move off in the same direction. Actually, let's put up. Right? I will show you what will happen. All right, so watch this here. Right? How do we apply principle conservation of momentum here? Right? What do we know? We know the momentum before collision is equal to the momentum after collision. So if I work this out and I add it up and think, I should get the same value here, right? Correct? That's okay. So let's work on the momentum here. Momentum is what? Mass by velocity, mass by velocity. So what's the momentum here? 4 multiplied by 3. What's the momentum here? 3 multiplied by minus 5. Very good. Why minus? Opposite direction, right? So this is 12 plus minus 15, which is minus 3 kg ms minus 1. Now, this momentum is supposed to be equal to this momentum, right? What's the momentum here? 4 multiplied by, would this 2 be positive or negative? No. And we said this way is negative, right? So that'll be 4 by minus 2 plus 3 by b, right? B in the positive direction. So when you work this out, you'll get minus 8 plus 3b, right? So minus 8 plus 3b is equal to minus 3. Dual max, you'll get 3b carry across the minus 8. You'll get minus 3 plus 8. Carry across minus, I get plus. So you'll get 5 is equal to 3b. B is equal to 5 over 3 meters per second. Okay with that? Yeah, Dylan? Right? So the momentum before is equal to the momentum after. Right? It have different scenarios where they stick up and they move together. They both go in the same direction. They both stop. Right? They are different scenarios. Right? This is just one particular scenario. Carry across this, they get 5 and divide by 3, they get 5. Right, Nathan? Huh? If I carry across with 3, like 3 here, you know. So I carry across minus 8, 3 plus minus 8. Sorry, 3 plus 8 because I move it across, it's 5. Then I divide both sides by 3 and I get 5. Okay? Yeah? Right? Copy it down. I will just squeeze in one of it down. Online, are you okay there? Next day, hopefully you remember this, and we're going to apply this now. Because the past people on this. Applying momentum and all the laws. Right? Your homework for me, I just wanted to read up on how momentum links to these laws here. Right, since we're having fun, just take one more. Huh? Go ahead, copy down. All right, so yeah, time it good. Someone time it real good. If I give it a little time there, so you could go back on the phone and message you again. One last one, everybody online, please message. All right, here's what happened. When they collide, let me say they stick up together. So they have one velocity. Let me see you work out that. So they have one velocity. Both of them have the same velocity. After collision, they stick up together. I'm gonna see how you will handle that. They have one velocity. Stick up together like one, right? Right, take your time and let's work on the momentum after and we're done. Online, just message your answer, right? Message what you got for V. Take your time. Right? If you're not sure, like how, just treat it as one. One big mark, right? Treat it as one big mark. Do a little maths and you are done. Pay attention to time, go get the right entire unit. Right? You have to write it low, yeah. Yeah, you have to write it low. Put the momentum before you put the momentum after. So just magically make them equal, right? All right, last one. And this little addition and we're done, right? So this one here is 5 multiplied by 2. This one here is 10 by minus 150. Right? And here is 15 by V. So when you work this out, 10 minus 150 is minus 140 is 15V. Or just put it around. 15V is 140. Right? And then divide both sides by 15. And you'll get V is equal to how much? Minus what? 9.33. Don't forget your SI unit. Right? So it means that they move off together in the negative direction, right? Minus 9. Huh? Oh, thanks. Okay? Are you okay with that? So the final velocity is minus 9.33. Are you okay with that? Okay? So next day, let's take another 2 minutes for you come watch the last 5 minutes of the class videos. Right? You'll do some views too. And then we start doing some past papers on it. Okay? So we're going to do past papers on this and apply Newton's law and then start energy next. Right? I'm organizing. Put it one time.